What is going on, everybody, and welcome to part 8 of our Deep Learning with Neural Networks TensorFlow and Python tutorial series. In this tutorial, what we're going to be talking about is simply adding more data to a model just to see what kind of impact that's going to have. So to start, we're going to be using the exact same neural network that we've been using since the very beginning, a very basic feed forward and back propagation deep neural network. And in the previous tutorial, what we did was we used that on about 10,000 samples of positive and negative labeled sentiment data, and our accuracy was about 60%, which is pretty atrocious. So now the question is, what if we added more data? So if you remember to the very beginning of the deep learning kind of tutorials, I mentioned that the two major changes for neural networks that occurred that brought neural networks back to the forefront, because neural networks are not new. Most of the models and concepts and core of neural networks that you're going to use are not new. But what changed was the availability of huge data sets and also the processing power of either GPUs or maybe even now with tensor processing units or whatever else people happen to come up with. Even Intel's coming up with CPUs that are more GPU-like. So anyway, it'll be an interesting future, but regardless, those are the two major changes. So what happens when we take that exact same model that we had been using, giving us horrible accuracy, and just throw a bunch more data at it? Like, what's going to happen? So we're going to use the following data set. It's the Sentiment 140 data set. Sentiment 140, there it is. So you can just Google that, or if you go to the text-based version of this tutorial, I'll have a link to it. But you can come here and download that data set. If you come down here, you'll see the polarity is either 0, 2, or 4. 0 is negative, 2 is neutral, 4 is positive. Now, if we're going to ignore this neutral because our previous training set didn't have neutral sentiment labeled information, that probably would increase accuracy significantly to use it, and maybe we will use it in a different tutorial. But for now, I just simply want to show the addition of more data and what kind of an impact that might have. So anyway, you'll grab that, and I will just say that all this code, everything will be available on pythonprogramming.net if you want to grab it. I am not going to go through line by line on this because nothing is changing as far as the concept or the deep neural network, so I don't really see a reason for us to go line by line again and just waste everybody's time. So we're not going to do that. And instead, I'm just going to run through the changes, what's different between what we've written in the past and currently. And then if you want, you can go to pythonprogramming.net and copy and paste that code or whatever if you'd like. So also, this dataset, since due to its size, it's going to run really slow on a CPU. So we're about to make the transition into using the GPU rather than a CPU. And you'll be able to always follow along on your CPU if you want, but you're not going to get the kind of accuracy that we're getting on a CPU. And if you did, you're going to have to wait like months to train some of these models. So anyway. So this is the pre-processing data. The first thing I'll note is, first of all, I wrote this function before I got to this function here, this convert to vector. And I thought I was going to do the same thing as before, where we converted to the training set immediately, and then we ran it through the networks. That's a faster way to train. That way you just have to convert to vector one time, and that's it. But on a much larger data set, the first problem that you're going to have is that you're not going to get away with that. You're not going to get away with making one huge file. I mean, you might, because this file didn't have to be too big for a hard drive. But recall, I think it was like, was it 100 times or 400? I can't remember how many more times large. I think we went from like 3 megabytes to I can't remember what it was. But if you've been watching, and it's been some time since I've filmed that, so I can't remember what those exact numbers were. But anyway, there's a huge increase. But anyway, so this one's not necessarily important. I'm just showing you the code that I wrote as I went through it anyway. But eventually we decided to kind of do this in line, and when we get to the actual network part, I'll bring this up again. But for the lexicon, it does kind of make sense to make that initially. And the way that I went about doing that is, first of all, you open the file via buffering, so you can kind of run through, and here, this is in bytes, so it's just 100,000 bytes. And then we're just going to iterate through this, and then every 2,500 lines, we're going to take all of the vocab from those lines, and then that's how we're making our lexicon. So in this one, just this file was labeled 2500 for that was one out of every 2500, and then 2638 is how many words are in this lexicon. So in this case, it's 2638. Again, this was to keep the model size reasonable, but generally language models, you're going to see lexicons like vocabulary sizes more like about 100,000 words, and yeah, about 100,000 words per language that you might need to know. So keep that in mind. Sometimes you can go down. You know, I've seen, like, if you look at TensorFlow, I think their language translation example is about 40,000, but it's based on a model that was like 160,000. Actually, it was even more than that. It was more than 200,000 total on both sides. But anyway, I digress. So this is still a very small model, but you have to, the bigger this number is, the much larger your network is going to be that has to be stored into memory. So anyway, keep that in mind. So then, yeah, this just gets commented out because you really only need to create a lexicon once, but obviously if you don't have it, you'll have to do that. And then we convert to vector, but for the training set, this is absolutely, I mean, you're going to make, I think the file size would be somewhere like 20 to 30 gigabytes. Oops, sorry. I don't have that much space on this dual boot, so that was just too big. You could save it to a different drive though, like, because you can access a different drive. But again, I kind of wanted to give you guys, after I got to this point, I was like, oh wait, well, this is actually a real problem, because a lot of times you're going to have a data set that is just simply too big for you to just store in your memory or something as you read it in. So you might as well do this in line. So we'll get to that in a little bit. Shuffle the data, same reason as before, you just have to shuffle it. So we're just shuffling that training data using this right here. And then the test data pickle, we're just making a quick pickle so we can very quickly test this framework. So that's that. Now we're going to go over to the actual neural network code here, and I'm trying to think if anything major changes. These are some notes. Like if I only used 200 data, it was 52% accurate. If I used 2,000 data, it was 62%. Both of these were 10 epochs each. 2,000 data, 63%, which was 15 epochs. And then by the time we hit 200,000 data, it was about 74% accurate, which you'll see soon enough. So batch size, you could make this bigger as well. It just depends on what kind of memory you're working with. In this case, I shrunk it down, I guess, to 2 layers. I don't remember at what point I did that, but I seem to recall using 2 or 3 layers didn't really make a huge difference. And for the most part, it never will. So depending on how complex your problem is, that's when you add layers, but adding layers is not going to necessarily improve your accuracy unless you've got a really complex problem or something. But for the most part, 2 layers is good enough to, because basically 1 layer would be for like linear data, 2 layer would be for nonlinear data, 3 layers would be for super nonlinear. But if you just keep adding layers, you're going to just overfit most likely your problem. But anyway, continuing along, simple neural network. Again, if you want, you can make this 3 layers and see what happens if you really want to do it. The saver object. So this is the way that you can save and restore TensorFlow models. So did it just know this? Freaking Google. Anyway, variables, creations, initialization, and all that. So you can come here and you can check out the documentation here. I will just note that this acts differently on the GPU version versus the CPU version, at least as I have found so far. So just depending on which way you use it, just kind of tinker with it. But you can look at their examples, but basically before you call the saver object here, you have to have some TensorFlow variables defined. Even though in your head you're thinking to yourself, well, maybe you just want to, and you're just calling the saver object so later you can restore a variable, but that's not good enough, because I guess maybe the variables are saved but not like the model and the structure. I really don't know. I'm not sure why you necessarily have to do this after the variables, but that is the case. So just remember that you need to do that. And then also you would do this outside of your session, but then to restore, you do that within the session. And then when you do restore, you restore what? The session, and then from where? Where was that checkpoint file? And again, we'll run through this in my code as well, but I just want to bring that up. And then obviously when you save it, you're calling the saver object same as before, only this time, again, within the session, you're doing some stuff, and then when it's time to save, you don't have to actually assign it to a variable, but you can just say saver.save. What are we saving? This session, and then to where whatever path you want. So that's the saver object. Also, I used this TFLog purely to log the epochs. I still haven't quite figured out, like, you should be able to store a TensorFlow variable that tracks the epoch number you are on. Not happening for me, so anyway, I think it's probably because, if you try to define it up here, maybe it's replaced. I don't know. I couldn't figure it out. If you want to figure it out and post below, like, how you're doing it, let me know, because I was like, I could not figure out why I couldn't make that happen. I tried so many things. So then I was like, well, I'll just make a log file that says, okay, you're on epoch X, whatever that happens to be. So yeah. Anyway, then when we get to the training, everything's pretty much the same. Don't forget to initialize all your variables before you would do that before you restore any sessions, just for the record. But anyway, here I'm just doing a quick try and accept with some lovely code that's just reading that TFLog file just to see what was the very last epoch. And then if we can't read that for whatever reason, we're just saying, yeah, we're on epoch 1. So if that file doesn't exist or whatever. Then coming down here, we begin iterating through all of our epochs. So in theory, like, sometimes people just run like infinite loops when they're training and they don't really care like how many total epochs, like the network will just run forever. And then sometimes you actually want to like limit however many epochs you want to do. So I mean, in theory, you might not even need the TFLog, especially on like much larger data sets, but whatever. Anyway, if the epoch is not equal to 1, so if we're not starting over, right, then we want to load the model, whatever that model is. So in this case, if the epoch is not 1, we're going to load model.ckpt. And then we're going to say, oh, sorry, I thought that said epoch equals 1. I was like, wait a sec. Anyway, epoch loss 1, whatever. And then we continue along. This just opens up the lexicon for us. So after the lexicon, we begin going through the Trainset shuffled via buffering again. This file was not huge necessarily, but you could be working with, say, a dataset that's like 500 gigabytes or something, so you can buffer through it. TensorFlow did have like a feed, like, I don't think it's called buffering. If I can pull it up real quick, I wasn't really thinking about it until just now. TensorFlow buffering, because they do have something for it, but I could not seem to get it to work. So feeding, reading from files, maybe it was batching, and maybe feeding. I think it was probably actually feeding. Or was this pipeline? I think I tried both of these, but I just could not get it to actually do anything for me. So I didn't find it to work out, but probably a better option would be to use this rather than my method if you can figure it out. I just couldn't figure it out. But anyway, reading in the file, and then we're just iterating through the lines as we're reading them in, working with the label is just that, and then the tweet, this, which is still a string, and then we convert it to words, we lematize it, we do the feature vector, same thing as we had done before. Nothing is different. Really, this is just simply an X, this is just simply a Y. So actually we're not even really using batches at the moment. But anyway, moving along. Saver.save, now we save it every time we're kind of like working through it. And same again, we're just resaving it to model.checkpoint. Print out the epoch whenever we're done, so it just saves per epoch. And then also, I'm writing to that epoch log file. Again, I'm positive there's a way you could do it with a TensorFlow variable and save it all to your session. I just could not figure that one out. It's just too complicated for my little brain. Correct accuracy, nothing really changes there. And then processing, or doing the test set, again, this one, just same thing as before. nothing really changes here either. So that pretty much stays the same. And then later on, we're actually not even going to use this because this happens at the end of a very long process. So I ended up actually just making a new function that is just simply test the neural network, and then we actually test the neural network. And then finally, before we actually test the neural network, I just want to pop on over to using the neural network, and then that I just added some functions here at the bottom. I think it's just, yeah, this function here. So use the neural network. So obviously, when you come up with a model that you're happy with, you might actually want to, like, rather than just training and testing it all the time, use the model, right? So in this case, this is a function that works. Basically, you just say use neural network. You pass a string like this one. I've got he's an idiot and a jerk, and this was the best store I have ever seen, or I've ever seen. And then the output, it's either going to print positive or negative. And all that we're doing here is we take that input data. We know we need to vectorize it, right? So we're loading in the pickle. We load in the model itself and have it to this prediction value. We run the session. We're restoring via a checkpoint file. I changed the name, by the way. This is just a checkpoint file that's been trained completely. The 74 just means it gives 74% accuracy. And then we go, let's see, where am I? Yeah, so we load that in, start off as epic loss is equal to 0. I'm not even, why is that even there? I'm like looking at this now and I don't know why we did that. I guess I just shaved it out and then I didn't think about doing this. There we go. Or it was a very late night and I was coding, and yeah. So anyway, so that's all you need. I don't know what we were do with the epics. And epic loss doesn't need to be there either. Saver.restore. So we restore that. We take the current words, we tokenize them, lemmatize them, do the feature vector for the word in the feature vector. So we're just making this feature vector. And then our result is equal, this is kind of an important line here, to, this doesn't necessarily need to be in parentheses, ses.run, and then we're asking what is the tf.argmax of prediction.eval feeddict, and what's the value that we're passing in here? We're just passing a simple value for x and its features. Done. And the other thing I'm going to have us do is this, right? Is it this? Copy that, and I do want to just print rather. Right. I do want to show y'all what the actual output from this is, because I don't think I've actually ever shown that yet in the videos. So anyway, I do want to show you what that actually looks like, because it's not 1 0 or 0 1. It's like a cajillion and a lesser cajillion or something like that. Anyway, so cool. So we'll save that, and I'm gonna come over here and save this one too. I'm not quite sure what we changed there, but anyway. So this one I'm actually not gonna run because the actual training takes forever, and I'm actually still on my VPS, but probably in the coming, maybe not the next tutorial, but from here on out, I will be almost certainly recording on my GPU version. So this takes a long time to run. So yeah. Anyway, I'm gonna open up terminal, change directory into let's see, desktop, and then I think this is like larger data, TF. Yes, this is where I want to be. So anyway, these files, by the way, both of these, the lexicon and the model, will be up on pythonprogramming.net. So if you want to just grab those two files just so you can like see it for yourself, they are there. Go to the text-based version of this tutorial and you can download them. As far as I recall, I think I actually saved them as straight just lexicon.pickle. Lexicons. How about model.ck? Trying to find them just to see if I put them up there and under what. Yeah, the model will be model.ckpt, and the lexicon is just lexicon.pickle, so they don't have these long notes on them. Feel free to add them if you want, but just keep in mind if you use this code, the text-based version of this tutorial has them correct. So if you are copying and pasting from pythonprogramming.net, you'll have the correct the correct names anyway. But just keep that in consideration, that's what they are. Anyway, So first we'll run Python 3 TF8 saving and restoring. And what we're going to do is not train the neural network. That's commented out. We are just simply going to test the neural network with that processed test set. So I'll run that. Test exactly 359 samples. Accuracy is 74.6518%. So again, all that really changed. One thing I did kind of note that did also change is we're kind of training one sample at a time here rather than training in batches. So that will make a slight difference, but that I could be completely wrong, but that should not be making this large of a difference in the accuracy. The main difference here is simply we have 1.6 million samples of data as compared to 10,000 samples of data. So next, what we're going to do is we're going to come over to TF9, and TF9 is just use the neural network, and this is going to let us actually like see how the neural network actually performs against actual string data. So I'm just using these two strings here. He's an idiot and a jerk. This was the best store I've ever seen. So now we can run that, and we can say Python 3 TF9 using the network. And there you can see the two outputs here. So the first one is negative, and then the next one is positive. And you can see how close, like these actually, both of these were actually very close to each other. It could have easily gone either way. But this one is smaller than this one. And that's kind of the point I was trying to make before, was that it's not going to be a 0 or a 1. It's going to be which neuron is firing the strongest. And in this case, it was the negative neuron, right? Because this one is the positive neuron. This is the negative neuron. They're very close to each other, but this one is firing strongest. Most likely because each of these words is relatively, you're going to see this was the store I've seen. Ever might have some weight, but it could go either way too. So most of these words are relatively useless. There's really one word here that means anything in terms of sentiment, and then over here there's two words, but we still have quite a few words that aren't. I don't know how idiot or jerk couldn't have swayed this a little more, but okay. Because what if we say he's an idiot? So just he's an idiot is positive, right? So yeah. Anyway, there's your 74% accuracy. So yeah, you can kind of play around with that if you want, but again, even 74% accuracy is really nothing that special. It turns out we need even more data and a better model. So this, traditional, just like a straight up feed forward back propagation deep neural network is not meant for language data. It just doesn't perform well in language data. So there are lots of other models and stuff that we're going to be able to possibly look into in the future that perform much better on language data. If you want to look into it, generally a recurrent neural network form of LSTM or something like that is going to perform better on language data. So yeah. Anyway, that's all for this tutorial. Just wanted to kind of run through the example of a much larger data set, but also kind of the little nuances like saving as you go. That way, like if your model takes a very long time to train, you don't lose everything because the power drops or something. Also, so you can actually use it. Like as this thing trains, if you wanted to, the training is going to take months, but maybe you could just use the model along the way or test it just to see how it's doing along the way. So there's that. And so obviously that's useful. Buffering in data or just working with large data sets is in general pretty challenging just because you have to figure out a way to get that data into your actual model. And the other thing that's really challenging, especially when you're trying to work on your GPU, is input-output. And that's why I think you'd probably rather be working with TensorFlow's input-output specifically, because it might be, and it most likely is, more efficient than straight Python code. So Anyway, I'll try to figure that one out a little more. If anybody else figures that one out, feel free to post an example of how to feed in this data using the TensorFlow method of reading in data, because I couldn't figure it out. But anyways, that's it. If you have questions, comments, concerns, whatever, feel free to leave them below. Otherwise, as always, thanks for watching. Thanks for all the support and subscriptions. And until next time.